Doctor Eloy, si nos ayudas a empezar.
Okay. Well, the Instituto Politécnico Nacional of Mexico welcomes you. Today, we begin with the high-frequency electronics talk sessions in the frame of the Institutional Chair Eugenio Méndez Docurro, 2020. The sessions of today are entitled High-Frequency and Terahertz Devices and Circuits, Perspectives on Emerging and Advanced Technologies, Part 1. We are sure that these talks will be very fruitful to the audience, and we thank the speakers and the public to attend this event. These talks will be held in English. El Instituto Politécnico Nacional les da la más cordial bienvenida. Hoy comenzamos con las pláticas de electrónica de altas frecuencias en el marco de la Cátedra Institucional Eugenio Méndez Docurro de 2020. Las sesiones se titulan Dispositivos y circuitos de altas frecuencias y terahertz, perspectivas de tecnologías emergentes y avanzadas. Parte 1. Estamos seguros que estas pláticas serán muy fructíferas para la audiencia y nosotros agradecemos a los expositores y al público por estar aquí. Debido al nivel internacional de estas pláticas, estas serán dadas en inglés. Muchas gracias. Now, Dr. Elena Acevedo, go ahead, please, with the first speaker.
Thank you, Dr. Eloy. Well, our first speaker is Dr. Pedro Carlos Feijó. Dr. Feijó obtained his BSc degree in physics and the MC degree in applied physics with a specialization on electronics from the Universidad Complutense de Madrid, UCM, Spain, in 2007 and 2008, respectively. He obtained his PhD in physics degree from the UCM in 2013 in the field of microelectronics fabrication. From 2014, he has been working in simulation of microelectronics devices based on two-dimensional materials at the Universidad Autónoma de Barcelona, Spain. He has done internships at IMEC in Belgium and Alto Illospito in Finland. Welcome, Dr. Feijó from Universidad Autónoma de Barcelona. Our speaker will present the topic, the theoretical limits of radiofrequency performance of graphene field effect transistors. Doctor, you have 30 minutes for your exposition. After this, we will have a question session of 15 minutes. Please, all the questions go to the end of the exposition, and the questions should be written written in the chat. And I'll pass the questions to the speaker. Dr. Feijó, please start your presentation.
Okay, thank you very much for your presentation. I will start sharing my computer. Okay, I hope you can already see my presentation. So I'm going to present this, as Dr. Elena Acevedo has said, the theoretical limits of radiofrequency performance of graphene field effect transistors. I would like to take the opportunity to thank the organizer of this conference for giving me the chance to spread the research that we do here at the Universitat Autónoma de Barcelona. So this is the outline of my presentation. I will start with the introduction, where I will try to justify the research that we do in the field of graphene. Then we will pass to the simulation, to the model that we use to simulate the different graphene field effect transistor at its performance. And then we will speak about the comparison between our models and some experimental work that is done by a group that collaborates with us. Then I will pass to some results that are a summary of how the different parasitic parameters, the parasitic parameters, how it affects the performance of the graphene field effect transistor, and finally I will extract some conclusions. Okay, so let's start with the introduction. Since its discovery in 2004, well, the discovery that it was stable at atmospheric pressure and so on, the graphene attracted a lot of interest in the field of microelectronics, since it has a very high mobility and a very high saturation velocity, as you can see in the presentation. In fact, if you compare the numbers of graphene to the ones in silicon, that is the material where all the electronics is currently based, you can see that the electrons inside the graphene are much more quick, are much more fast than in silicon. So this would mean that the devices made of graphene could achieve to higher frequencies than silicon. In fact, the main important thing in graphene could be to reach the gap that is above the radio frequency. As you can see in this image, let me show you, below the terahertz regime, there is the radio frequency that is used in telecommunication, and above there is the visible light, where the photonics takes place. But in the middle, there is a gap that could be of use in the graphene technology. And why it is important to reach this gap? Because it has some very important opportunities that would be good for some fields like medicine or security or so on. Okay, and why didn't we use this region of the spectrum before? Because there were no any device that could be able to use it. So there were necessary some new materials to reach this gap, and graphene is one possible choice. Okay, and how do we measure the high frequency performance? So imagine we are going to use the graphene inside transistors, and this would be a typical structure of the transistor with a gate and a source and a drain terminal. Remember that the voltage that you put at the gate controls the current that goes from the source to the drain. Okay, there is a fourth terminal, but we are not going to care about it because it is kind of a reference terminal. So the most important ones are these three. And when we are talking about high frequency performance, what we do is to use the transistor as a two-port network. A two-port network, we use the source terminal as a source, as a reference, and then we introduce a signal at the gate and we get an output at the drain. Okay, so what we are going to do is to use this kind of a scheme. We will put a signal at the input, and then we will get an output. And what do we care about this? What we need is to maybe to multiply by a factor to increase the factor of the current that the ratio between the drain current and the gate current, or to increase the power. So what we are going to analyze about these transistors is the possibility to use the current gain and the power gain. Okay, and how can we measure the current gain and the power gain? What we are going to use is the figures of merit of high frequency performance. When we attend to the maximum current gain, we define the cutoff frequency as the current as the frequency that gives us a current gain of 1. On the other hand, if we are talking about power gain, the maximum oscillation frequency is the frequency that gives us a power gain of 1. So these two figures of merit, the cutoff frequency and the maximum oscillation frequency, is going to give us a view of, well, a limit, I would say. It's going to give us a limit about the frequency that can be used in for a transistor. So what we want now is to get cutoff frequency and maximum oscillation frequency in the range of the terahertz. Okay, if you look at this graph, these are typical graphs about the current gain and power gain. When this current gain reaches the unity, then what we get is the cutoff frequency. If we are discussing about power gain, then when it gets to 1, the maximum oscillation frequency comes to place. Okay, so we are going to discuss the possible cutoff frequency, maximum oscillation frequency that are able to appear. And to put you in the context, to speak about a little state of the art, with the graphene transistors, what the maximum cutoff frequency and the largest maximum oscillation frequency that have been achieved are 427 gigahertz for a 67, sorry, graphene field effect transistor. This is the length of the channel, that is the distance between the source and the drain. While the maximum, well, the largest, the highest maximum oscillation frequency is 200 gigahertz. On the other hand, there are currently some materials that are available to be built and to be bought even in shops or so on, in electronic shops, made of indium phosphide and silicon, and they reach very high frequencies as 1 terahertz and 500 gigahertz. But in fact, we expect that the graphene can overpass these limits. So this is why we are still working on graphene and trying to make graphene a material in the terahertz technology. So let's see now how we study this material, this transistor based on the graphene. What we use is a self-consistent model that consists in 2 equations, the Poisson equation and the current continuity equation. We start with an initial guess, that is a distribution of charge around the channel, and then with this charge in the channel, we calculate the electrical field through the Poisson equation, and then with the current continuity equation, we get another charge distribution that we introduce again in the first equation. With this, what we have after some iterations is a solution, a stationary solution that gives us the current and the charge distribution in the channel. Okay. Together with the equation that we have already seen, the Poisson equation and the current continuity equation, we solve also the self-heating effect. When you are using a transistor, between the source and the drain there is a current, and sometimes the power dissipated in this graphene cannot spread, cannot go, and then the temperature of the graphene rises. In fact, the rise of the temperature of the graphene makes that the saturation velocity decreases according to the models that we use, and also the current concentration can increase. So the temperature is going to limit the performance of our device. We will see later how much it limits the performance. We use a very simple model with where the temperature rise is proportional to the power dissipated and thermal resistance. Okay, the power dissipated inside the graphene is just the current multiplied by the voltage between the source and the drain. These are typical maps that we get with the with the model that we use. This is the current, the drain current, as a function of the gate voltage and the drain voltage. And we see this kind of maps. For example, if we make a cross section, this dashed blue line would give this line here. This is a transfer curve of the of a graphene transistor, while this dashed green line is an output characteristic. Okay, with the typical kink that can be seen as the drain voltage increases. Apart from the current, as I have said, our model gives us the charge distribution in the transistor, so the charge at the terminals can be calculated, for example, the charge at the gate and the charge at the drain. So now that we have seen how we get the stationary characteristics, we pass to the high frequency. How do we calculate the high frequency performance? What we do is to apply, well, we choose firstly a bias point, and then over this bias point we apply a small signal that is a voltage, a small voltage, and then what we get is a small current, a small signal current. And if we use the current approximation, what we do is to imagine that we are on this slope of the curve, of the DC curve. And this is what we call the quasi-static approximation. And we use the quasi-static approximation to get the small signal model. Okay, the most important parameters, well, the necessary parameters for the quasi-static model, for the small signal model, are the transconductance, the output conductance, and these transcapacitances. In fact, the transconductance and the conductance are the rate of change of the current as a function of the gate voltage and drain voltage, while the transcapacitances are the rate of change of the charges as a function of the voltages. Okay, so this would be, after the simulation, the intrinsic small signal model from the quasi-static approximation with the different transcapacitances and transconductance and output conductance. Okay, so this is a very simple model, and with this we will be able to calculate the radio frequency performance, that is the cutoff frequency at the maximum oscillation frequency. This is the intrinsic model that we have already seen, and apart from this, to calculate the extrinsic model, the model that we can measure, we have to add some parasitic elements that they are going to limit the radio frequency or high frequency performance of our material, of our device, but they are unavoidable. And we will see how they affect the behavior of the device. In particular, we speak about series resistances at each one of the terminals, the gate, the source, and the drain, and also parasitic capacitances between the different terminals. For example, between the gate and the source, between the drain and the source, and between the gate and the drain. Okay, so these 6 parameters are going to be parasitics that are going to limit the performance of our devices. So right now I'm going to try to simulate or show you how to get the typical parameters of a transistor from the experimental work. To do this, we have used a device fabricated at the Chalmers University in Sweden, in Göteborg, by Professor Borowiak's research group. You can find all the details of the fabrication in this article of nanoscale device advances, published at the beginning of this year. It is a device with a channel length of 500 nanometers. That is the distance between the source and the drain is 500 nanometers, and a width of 15 microns with 2 fingers. And finally, they use as a gate oxide, aluminum oxide of 22 nanometers in thickness. So the first part of everything is to take the transfer curve, and from the transfer curve here, these the symbols correspond to the measurements, while the line to our simulations. And from this we can get the flat band voltage, that is the point of the minimum conductance. We can get the mobility that goes to 2000, that it is a typical mobility for graphene transistors, and the contact resistance, that is the Servier resistance at source and drain, and the paddle concentration. The paddle concentration is the minimum carrier concentration in graphene. It is done because of the irregularities across graphene. Once that we have these parameters, we can, with with the output curves, that is the current as a function of the drain voltage, what we get are the density of defects, that it is very low, the density of defects of the interface between the graphene and the different and the substrate. Phonon energy of, well, the phonon energy is directly related to the saturation velocity, and it gives us how the electrons interact with the phonons, and the thermal resistance that is related to the self-heating effect in transistors. Also, apart from this, we have measurements of the small signal parameters. That is the matrix, the admittance matrix of the device. It is possible to be measured. And with this, we have the gate resistance of 10 ohms and the parasitic capacitances at the input and at the output. This one, the one that is from gate to drain, is 0. Doesn't have a contribution according to our results. Okay, and from these parameters that we have already obtained from these, we can calculate the high frequency performance. And in fact, if you compare the simulated high frequency performance and the symbols that correspond to the measurements, you can see that we get a very, very nice fit between both of them. Okay. In fact, this device is very good in terms that for this channel length, it arrives to 40 gigahertz, that it is quite high. Okay, and this is what we are able to simulate. And another, on the other hand, we have another confirmation that our simulations are good, because if you measure the capacitance, the parasitic capacitances, the corresponding values that we have obtained with our simulation are very close. These signals can be obtained with a device that have been fabricated very similarly to the one that we measure with graphene, but without the graphene layer. So with this open structure, you can measure capacitances that are going to be the parasitic capacitances that appear at the source and drain. So from now on, we have seen well, until now we have seen how to simulate the device, but now we are going to see how the different parameters affect the performance, the high frequency performance. So if we simulate the maximum oscillation frequency and the cutoff frequency of the device that we have seen that can be fabricated, we get these kind of maps as a function of the gate voltage and the drain voltage. And here you can see that there is a maximum and optimum bias point, where the maximum oscillation frequency and the cutoff frequency are optimal. This corresponds to a bias point where the channel is completely full of electrons, and where there is a depletion of carriers very close to the drain. Okay, this would be the positional on the channel. Here would be the source. Here would be the drain, and you can see that there is a depletion of electrons very close to the drain. So we are going to concentrate in this bias point to see how the different parameters behave, but in fact, using other bias point would give the same results. Okay, so let's start with the contact resistances. We have seen how much the series resistances at the source and the drain affect the maximum oscillation frequency at the cutoff frequency. And you can see that, well, in this graph, the blue and red curves correspond to the series resistance at the source and the drain source, the drain resistance respectively. But if we decrease both of them, they give us our green line. This dashed line would correspond to the value that we have measured. So, actually, I have stated this point that corresponds to the typical values, typical minimum values that can be obtained in graphene technology. Okay, of 100 amps per micron. So you can see that if you reduce contact resistances, you can increase the maximum oscillation frequency from 40 to 48. So there is a slight increase in the maximum oscillation frequency if the contact resistance is reduced. But in fact, if we go to the gate resistance, the maximum oscillation frequency can go from 40 gigahertz to almost 90 gigahertz. So even reducing 1 order of magnitude the gate resistance, you can obtain a very nice increase of the maximum oscillation frequency. In fact, if you look at the cutoff frequency, you can see that it doesn't affect the cutoff frequency, but it affects a lot the maximum oscillation frequency. We can also compare the influence of the different parasitic capacitances. You can have here 3 curves with 3 colors. In fact, if you look at the maximum oscillation frequency, you can see that the parasitic capacitances are not going to affect this parameter, but the cutoff frequency is slightly affected. For example, if a reduction in the parasitic capacitance at the gate should slightly increase the cutoff frequency from maybe 28 to 30. So the amount of the quantity that we can gain is not very high. We can also discuss about the effect of the self-heating. Here there are the graph that we have already seen with self-heating, where there are some bias, where the maximum oscillation frequency and cutoff frequency are maximum. Okay, instead, if we are not considering self-heating, there will be no maximum, but no absolute maximum. There will be no relative maximum, I'm sorry. But absolute maximum. So the frequency that we are going to achieve is going to be higher for all biases. So if we are able to make the heat go from the device, for example, substituting the substrate by other with a higher thermal conductivity, we are going to get higher higher maximum oscillation frequency and the cutoff frequency, that is high frequency performance. And it is going to be limited by the maximum drain voltage that we are able to apply. It's not going to be limited by the self-heating, of course. And finally, we can see how the high frequency performance can be scaled as we reduce the distance between the source and the drain. Okay, as we reduce from 500 nanometers to 50 nanometers, we can see that the cutoff frequency increases up to maybe 500 gigahertz and something like 700 gigahertz for the maximum oscillation frequency. You can compare this with the maximum values that were obtained experimentally in previous research. And you must take into account that these curves are obtained assuming that the thermal resistance and also the series resistances at the terminals as constant. But probably as you get a lower length, these quantities are also going to be scaled. So probably at this point, we will have other limitations. But in fact, if we work with this and with the reduction of the channel length, we probably will be able to get higher, well, we will be able to work at the terahertz regime, that is 10 to 3 gigahertz. Okay, so thank you very much. I will finish with the conclusions. So we have developed a self-consistent grid diffusion model that includes the self-heating, and from this we can obtain the charge and current stationary curves. That means that we can get the DC curves and compare them with the experiment. From the quasi-static approximation, we can get a small signal model to calculate the high frequency performance of these devices. We have compared this model with measurements of performance of 500 nanometer graphene FET transistor, and we have studied the different the impact of the different parasitic elements, the series resistances, the parasitic capacitance, and also the self-heating on high frequency performance. Finally, we have seen that the maximum oscillation frequency and cutoff frequency of graphene transistors could reach the terahertz regime. We expect that it could be better than silicon and indium phosphide transistors. But in order to do this, what we have to do is to work on the gate series resistance and the thermal resistance to maximize the high frequency performance. So thank you very much for your attention, and I am currently open to any question that you may pose. Thank you.
Thank you, Dr. Feijo. You present a great speak. We have one question in the chat. Aníbal Pacheco says, in slides 26 and 27, could you please share your slides 26 and 27, please?
Mm-hmm.
You have shown that RG and CPGD have certain influence on the high frequency figures of merit. These parameters are closely related to the number of gate fingers of the device. There could be a trade-off between RG and CPGD to find either higher FT or higher maximum frequency, depending on the application.
Well, first of all,
yes.
No, sorry, I thought that the question was already finished. Well, what it is important is to reduce the gate resistance because this CPGD, we can see that the influence is not that big. So it is much more important to reduce the gate resistance than the capacitance, the parasitic capacitance.
Okay, thank you. He says, do you know why the technology groups only fabricate G-FITs with 2 gate fingers?
Well, because they are easy, but of course there are other approaches.
Okay, thank you. And the other question is, what would be the limitation of increasing, for example, to 40 gate fingers as standard fits?
Well, the main limitation is that this is a prototype, but well, they are done on top of pieces of graphene. So you don't have a very big graphene where you can do whatever you want. You are limited to the size of your piece of graphene that you have on your wafer, on your substrate.
Okay, thank you, Doctor. There is another question. He says, there is an spacer ungated region between source drain with the
Yes,
gate.
there is a space. Yes, I haven't talked about it because I wanted to keep this talk something simpler. But in fact, there is a space between the source and the gate, and the yes, and it is something like 100 nanometers.
Okay, and the question is, does this ungated region with no gate control over the channel has any influence on the RF performance?
Yes, of course, especially. Okay, yeah, probably it has a very big influence on the resistances that at the gate, at the source and the drain. But it's included there.
Okay, and there is another question. What if the device was fabricated on a back gate, oxide mesa surrounded by silicon with better heat dissipation properties?
With better heat dissipation properties. Well, I would say that the self-heating effect is not something that the experimental scientists are taking into account right now very seriously. Right now, what they want is just a device that works, and they don't care much about the self-heating. In fact, the temperatures are not being measured. Our model can predict the temperature of the graphene, but still the graphene temperature cannot be measured. So it is difficult to say. I would say that, well, we have a model to calculate the thermal resistance, but in fact it's not, well, we don't trust it too much. We have to work on it.
Okay, thank you. A second question, what about the thermal capacitance? Does it impact on the RF performance?
Well, according to our estimations, the thermal capacitance is very, very, very low. So it doesn't have any impact. We have worked about it. The impact could be that it could affect the high frequency performance, in fact. But what we have seen is that if you are calculating the small signal parameters, what you have to do is to consider that the temperature is constant. If you consider that the capacitance is high, then the temperature would change as you change the voltage, and then the small signal would be affected. It is something that we are working on it, but until now, what I can say is that the capacitance, the thermal capacitance of the of the transistor doesn't affect too much the high frequency performance.
Okay, thank you. There is another question here. The contact resistance values are in ohms, centimeters, or ohms, micrometers?
Yes, I'm sorry for this. You're right. The resistances must be always in ohms, not ohms per centimeter. But the typical, when you are talking about the contact resistance, you must take into account that you have a width. So the typical value that you give is the multiplication between the contact resistance and the width, because that way you can scale it.
Okay, thank you. Could you perform a simulation in the time domain?
Sure.
Okay, that is the question. Dr. Eloy, do you have some questions?
Just one question. First of all, Dr. Feijóo, for your excellent presentation. It was very, very interesting. Just one question. How the lack of energy band gap in graphene affects high frequency performances?
Well, the lack of gap in graphene affects the possible application in logic, but not at high frequency. What you need at high frequency, let me show you the transfer characteristic. Okay, the blue curve here gives you the transfer characteristic. If it were a band gap, you would have at one side of the curve something like this, but then something that goes to zero. Okay. At high frequency, you are working in this part of the curve, so you don't care about the gap.
Okay.
So it is not that important.
Okay, that's unimportant. Okay, thank you.
Thank you very much.
Thank you, Dr. Marilena.
Thank you, Dr. Eloy. I think there is no more questions, and we are on the time. And Dr. Feijóo, thank you very much for your presentation. And we are awarding you this diploma. I'm going to share it. Okay. Here we have the diploma. El Instituto Politécnico Nacional, Cátedra Eugenio Méndez Docurro, otorga el presente reconocimiento al doctor Pedro Carlos Feijóo Guerro por su participación en el seminario en línea denominado High Frequency and Terahertz Devices and Circuits, Perspectives and Emerging and Advanced Technologies, Part 1, con la conferencia de Theoretical Limits or Radio Frequency Performance of Graphene Field Effect Transistors, llevada a cabo los días 26 y 27 de noviembre de 2020, la técnica al servicio de la patria. Thank you very much, Dr. Feijóo.
Thank you.
Okay. And we are going to go to the next speaker. Okay. Our Dr. Mavrodekis, are you ready?
Can you hear me?
Yes, doctor. Okay, I'm going to introduce you.
Thank you.
Okay. Dr. Nicholas Mavrodekis was born in Chania, Crete, Greece in 1981. He obtained the diploma in electronic and computer engineering, the MSc degree, and the PhD from the School of Electronic and Computer Engineering in Technical University of Crete, Chania, Greece, in 2006, 2010, and 2016, respectively. He has been an invited researcher with AMS, Austria, 2010 to 2011, and with ADMOS, Germany, in 2012. He had been a member of the AKB3 Advanced MOSFET Compact Model Development Team since 2010 to 2017, and he has the researcher in charge for complete extraction of AKB3 model at many projects with industry. He has been a research associate with the School of Electronic and Computer Engineering at Technical University of Crete in Greece from 2010 to 2017, emphasizing noise characterization and compact modeling of micro and nanoelectronic devices. Currently, he's a postdoctoral research at Autonomous University of Barcelona, and he focuses his research is the compact modeling of noise in graphene and 2D material devices. He has authored or co-authored more than 20 articles in peer-reviewed scientific journals and conferences. Well, welcome, Dr. Mavrodekis from Universidad Autónoma de Barcelona. Our speaker will present the topic, one under F, noise modeling in microwave graphene transistors. Doctor, you have 30 minutes for your exposition. After this, we will have a question session of 15 minutes. To the audience, please, all the questions go to the end of the exposition, and questions should be written in the chat. Dr. Mavrodekis, please start your presentation.
Good morning and good afternoon to everyone. My name is Nicholas Mavrodekis and I'm a postdoctoral researcher at the Department of Electronic Engineering at the Autonomous University of Barcelona in the group of Professor David Jimenez. I would like to thank a lot the organizers for inviting me to give this talk. The title of this presentation is Bias-Dependent Modeling for Low-Frequency Noise Mean Value and Variance in Single-Layer Graphene FETs. So, the basic objective of our work is to investigate thoroughly the low-frequency noise in single-layer graphene FETs, to see from where it stems, and to study its mean value and statistical behavior. The final goal was to create accurate physics-based compact models that can be used in circuit simulators. But why low-frequency noise is so significant? First of all, it can be a severe barrier in circuit design, both in analog and RF applications, as it can be up-converted to phase noise in voltage control oscillators, for example. Furthermore, it can limit the sensitivity of chemical and biological sensors or even optoelectronic devices, which are some of the most significant applications of graphene. Last but not least, it can be proved a very useful tool for characterizing the reliability of the devices. In fact, the quality of graphene is closely related to the level of noise, because the trapping-detrapping process, which is one of the most important generators of low-frequency noise, can be easily activated through broken bonds in the graphene. Let's now see the general outline of this presentation. First of all, we are going to theoretically research low-frequency noise in graphene FETs. See in general what are the noise sources in semiconductor devices, and then, more specifically, what are the contributions to low-frequency noise, especially graphene FETs. So, we have the carrier number fluctuation effect, or delta N model, which generates noise due to trapping-detrapping effect in the oxide of the device. Mobility fluctuation effect, or delta M model, on the other hand, considers noise as a result of the fluctuations in bulk mobility and is usually expressed by Hood's empirical relation. Finally, contact resistance can also have a contribution to low-frequency noise, especially away from Dirac voltage. Afterwards, the low-frequency noise mean value and variance models will be derived and presented. Then, the graph FinFETs under test and the measurement conditions will be shown with two different kinds of devices used in this work, solid-state gated and liquid-gated ones. The first ones are short-channel devices provided from IEMN group from University of Lille in France and Professor Henry Happy, and are used for the extraction of the mean value low-frequency noise model. The second ones are long-channel liquid-gated devices provided from ICN2 Institute from Barcelona and Professor José Garrido, and are used for the extraction of the low-frequency noise variance model. Finally, we will demonstrate the validation of the models with data, both for the mean value and variance of low-frequency noise, and we will end up with some conclusions. The main noise sources in transistors are depicted in this slide. So we can see thermal noise, independent of frequency, above corner frequency Fc, while below Fc, low-frequency noise dominates. Low-frequency noise can either be in the form of random telegraph noise for very small devices, or in the form of flicker 1/f noise for longer devices, which is inversely proportional to frequency, as it can be seen from the plot. Let's now proceed with the modeling of low-frequency noise, and firstly with the carrier number fluctuation model. As mentioned before, carrier number fluctuation effect is created by trapping-detrapping process in the oxide of the device. Each such trap can create a random telegraph signal which corresponds to a Lorentzian spectrum. In small devices where number of traps are few, random telegraph noise prevails. On the contrary, in large devices where traps are a lot, the superposition of such uniformly positioned Lorentzians can generate 1/f noise, as can be seen from the plot. It is important to mention that in our data or in any other low-frequency noise data reported in literature, no random telegraph signal noise has been observed in graph FinFETs so far. In order to implement a model for low-frequency noise, a good IV graph FinFET model was needed, and such a reliable chemical potential-based model has already been developed by our group. Now, initially, we made some approximations in order to make equations simpler. So, quantum capacitance CQ was considered linear with the chemical potential Vc according to this expression. Regarding noise modeling, our general methodology was based on dividing the device channel in very small slices, where each one of them is a local noise source, and all these local noise sources are considered uncorrelated. The relative current fluctuation is given by equation 1, where QGR is the graphene charge, QT is the trap charge, and with N are the densities respectively. Graphene charge is calculated as here, where R0 is the residual charge, which dominates at Dirac voltage or charge neutrality point CNP, and can be extracted accurately from IV data. By applying charge conservation law, you can take equation 2, where Q top back and C top back are the top back oxide charge and capacitance respectively, while with C is the sum of the top and back oxide capacitances. Equation 1, because of equation 2, is transformed as here. And then from here, you can calculate the power spectral density, or PSD, of the local noise source, which, as you can see, it has a bias-dependent term, while S delta NT square is a constant term called trap charge density fluctuation. Here, NT small is the trap charge density, NT capital is the oxide volumetric trap density per unit energy, which is also used as a low-frequency noise mean value model parameter, and lambda is the tunneling attenuation distance. This proposed methodology was first published in Nanoscale Journal 2 years ago. Since the devices under test are short-channel devices, short-channel effects like velocity saturation and how they contribute to low-frequency noise shall be considered. In this work, we use a two-branch velocity saturation model, where, as you can see from this relation, U sat is constant near CNP and inversely proportional to chemical potential away from CNP. Drain current can then be calculated as here, where the denominator of drain current is called L effective and shows a contribution of a loss saturation to drain current. Then from here, the relation that gives the integral variable change from X to Vc, which is essential for the extraction of low-frequency noise models, is derived. The effect of a loss saturation on low-frequency noise comes from the second term of this equation, as well as from L effective, as we are going to see. In order to calculate the total drain current noise, we must integrate all local noise sources from source to drain. By changing integration variables from length to chemical potential Vc, according to the equation we saw just before, we end up to this integral for a delta n model with GVc a normalized drain current term. This integral can be solved analytically and provide us a compact solution. Let's proceed now to the delta M and delta R mean value models implementation. Regarding Hood's model, the same procedure as before is followed. So the power spectral density is calculated locally in the channel by using the empirical Hood's formula, which shows an inversely proportional to graphene charge behavior, as you can see in this expression. Alpha H is the Hood's parameter, also used as a low-frequency noise mean value model parameter. Again, by integrating along the channel, an analytical solution can be obtained. Now, a simple series-resistant low-frequency noise model is used for contact-resistant contribution taken from models for CMOS devices, where SDR² is also used as a model parameter. To calculate the total low-frequency noise model, we just need to add the three mechanisms that were analyzed before: the carrier number fluctuation effect, the mobility fluctuation effect, as well as the series resistant contribution. The analytical low-frequency noise mean value model presented here is published in ACS Applied Electronic Materials Journal. So after finishing with the demonstration of the mean value model, we shall proceed to the variance model. While there is a significant number of works regarding low-frequency noise mean value modeling in graph FinFETs, no studies are available that deal with the low-frequency noise variability in these devices, even though this variability is equally significant to its mean value. The large deviations of low-frequency noise observed in graph FinFETs makes it important and urgent to develop statistical low-frequency noise models to investigate the physics behind this variability. In the present work, such a new physics-based statistical compact model is proposed for the first time for the variance of normalized with area and divided by squared drain current output noise. This quantity is often used in similar works in CMOS technologies, since it follows an 1/area scaling, and that is the reason why we also use it in this work for graph FinFETs. Low-frequency noise deviations in graph FinFETs stem from the variations of the parameters of the physical mechanisms that generate low-frequency noise and not from IV quantities. These parameters are the number of traps NTR for the carrier number fluctuation effect and the Hood's parameter alpha H for the mobility fluctuation effect. The process for the derivation of the variance model is similar to the mean value model. Thus, the variance is calculated locally in the channel for each low-frequency noise mechanism in order to ensure that its drain current deviation delta ID, caused by a fluctuation such as a specific trap, at any tiny area of the channel will contribute independently. Then, the integration along the channel leads to an analytical compact solution with the help of the chemical potential-based model that we have already mentioned. It is important to say that applying fundamental laws of statistics, as here, will be proved very useful for the extraction of the variance model. Here, Y might be number of traps NTR or Hood's parameter alpha H, where number of traps equals to the area times the trap charge density. The normalized low-frequency noise local in the device channel for a slice delta X for delta N effect is given by this expression, while the total low-frequency noise is calculated by integration of the local noise along the channel as here. Then, by taking the variance of this equation, we have the basic expression to start the extraction for variance model. Since local noise sources are considered uncorrelated, and since integral is in fact a sum, variance can get into the integral as here. In solid-state oxide FETs, a number of traps is known to follow Poisson distribution, which means that its variance equals to its mean value. Then, if the equation of the integral variable change that we saw before is also applied, we can take this integral for delta n variance model, which can be solved analytically and give us a compact solution. Regarding the delta m low-frequency noise variance model, a similar procedure as in delta n case is followed, which ends up in this integral, which can be also solved analytically. Since there are no information for the value of variance of Hood's parameter in literature, we can assume that it equals with this expression in order to ensure that we have the same 1/area scaling as we did with delta n variance model. N alpha h here is a specific density used as a low-frequency noise variance model parameter. Now, in order to calculate the total variance, the delta n and delta m variances must be added under the assumption that they are uncorrelated. This assumption does not error a lot since delta n and delta m are dominant at different operating conditions. This analysis here has been published in Nanoscale Advances journal. While number of traps follow a Poisson distribution in silicon oxide devices, as we said before, it is experimentally shown in this work that this is not valid for the liquid-gated devices under test. This might be caused both by the electrolyte graphene interface in graphene FETs under study, and in general by the premature state of the graphene FET technology development, which could permit external factors to influence the performance of the devices. Thus, NTCOF is defined as a new low-frequency noise variance model parameter. In general, variance model parameters NTCOF and N alpha h are extracted from low-frequency noise variance data, but their value can also be confirmed by extracting the low-frequency noise models for every measured sample and then calculate the variance and mean value of NTR and alpha h, as it will be shown later. Finally, low-frequency noise data has been shown to follow log normal distribution many times in CMOS devices according to this expression, and here it is shown for the first time in graphene FETs. After finishing with the presentation of the models, we can now proceed to the description of the devices under test and the measurement setups. As we mentioned before, two different kinds of devices and measurement setups are used in this work. The first one is provided by IEMN group and is used for the low-frequency noise mean value model validation. In more detail, IV and low-frequency noise data were measured for 6 different solid-gated graphene FETs with a width of 12 micrometers and for 3 available channel lengths, a length of 300 nanometer for A300 and B300 devices, a length of 200 nanometer for A200 and B200 devices, and a length of 100 nanometer for A100 and B100 devices. The gate voltage was swept from 0 to 1.4 volts, covering regions both away and near CNP. Moreover, 5 different drain voltage values were recorded, VDS of 30 millivolts, 60 millivolts, 0.1, 0.2, and 0.3 volts, in order to cover the low and high electric field region, which is crucial for studying the low saturation effect on low-frequency noise. The second set of graphene FETs and measurements was provided by ICN2 Institute and is used for the validation of low-frequency noise variance model. In more detail, on wafer low-frequency noise and IV measurements were conducted at top solution-gated single-layer graphene FETs at 3 different device geometries: a geometry of 20/20 micrometers, a geometry of 50/50 micrometers, and finally a geometry of 100/100 micrometers. Gate voltage was swept from strong P-type to strong N-type region, including the CNP, with a step of 5 millivolts, while drain voltage was kept low and constant at 50 millivolts. A significant number of samples were measured for each available geometry in order to ensure that we have adequate data to characterize low-frequency noise statistics. In more detail, the analysis took place at around 20 to 25 samples from geometry 20 over 20, 25 to 28 samples from geometry 50 over 50, and 45 to 53 samples from geometry 100 over 100 after the exclusion of any outlier. The reason why the number of samples is not constant for each geometry is that some measurements might behave as outliers in some specific bias conditions, but not in the whole gate voltage range. Now, low frequency noise was measured for frequencies from 1.5 Hz to 2.5 kHz in all cases, while in order to study the bias dependence of low frequency noise, we had to calculate it at 1 Hz, and this was done by an averaging from 10 to 40 Hz. Let's proceed to the results now, and firstly, regarding the low frequency noise mean value model and the first set of devices and measurements. The IV model is presented in this slide since low frequency noise expresses the fluctuation of current, thus the absolute ID has to be well described. Drain current is shown in these plots for all available devices versus effective gate voltage, and at every plot, all the available drain voltages are shown. The fitting of the model, shown with solid lines, with experimental data shown with markers, is of high quality, both near and away CNP at p-type region. As you can observe, there is an asymmetry in drain current data at high gate voltages since they are lower in n-type than p-type region, and this can be explained either by a different mobility at the two operating regimes or by a parasitic PN or NN diode, which is formed between the channel and the contact when the device is biased in the P or N region respectively. And this can give rise to different contact resistances. The model, on the other hand, is symmetric, as you can observe, so it can provide identical behavior at P and N-type regimes away from CNP. The best fit was achieved at the whole P-type region near CNP and up to a value of effective gate voltage equal to 0.1 volt in N-type regime. We focused our attention on this region because it presents the highest transconductance, which, as we know, is a crucial figure of merit for RF applications. Regarding the low-frequency noise model validation, normalized drain current noise divided by square drain current at 1 Hz is shown in these plots versus effective gate voltage for all the graphene FETs under test. In the left subplot of each plot, lowest and highest drain voltages are shown, while in the right subplot, the rest of them. Markers again represent the data and solid line the model, while with dashed line, the model without the effect of velocity saturation is presented, which is also called a long channel model. As you can see, in all cases, data follow the well-known M shape with a minimum at CNP, and the model also follows this trend. It has been shown in our published work that delta M is significant near CNP, following a lambda shape, while delta N is responsible for the M shape. Also, contact resistance RC increases low-frequency noise at higher P and N-type regions. What is also of utmost importance is that the low-frequency noise data at higher electric fields are importantly reduced due to the velocity saturation effect, and the total model captures this reduction without the need of any fitting parameter. In more detail, as you can observe from the highest VDS case in left subplot of each plot, solid lines, which are the total model, fits the data, while long channel model with dashed lines overestimate low frequency noise data. Here in this table, the extracted IV and low frequency noise parameters are presented for every device under test. The first 4 parameters, mobility, effective gate voltage, residual charge, and contact resistance, are extracted from low drain voltage IV data, while at high drain voltage IV data, the phonon energy H omega parameter, which is related to the velocity saturation effect, is derived. Regarding low frequency noise, whose parameter is extracted from CNP, and then NT is also derived from the peaks of the M shape. Finally, SDR square is extracted away from CNP. The above three low-frequency noise parameters are derived at low drain voltage regime, and the good fitting at higher drain voltage is achieved with the value of H omega extracted from IV data. In general, the proposed low-frequency noise mean value model is proved to be very consistent. Both delta N and delta M mechanisms contribute at different operating conditions, and this is covered by the model. Finally, velocity saturation effect results in the significant reduction of low-frequency noise at high electric field regime, and the model precisely fits this behavior. Let's proceed now to the results regarding the low-frequency noise variance model and the second set of devices and measurements. The IV model is presented in this slide, where in the upper plots for all the three devices under test. Again, the markers represent the mean drain current data from all the samples, while the lines represent the model, which is extracted accurately in all regions of operation. Bottom left plot shows cumulative distribution function, CDF, of the natural logarithm of normalized with area and divided by square drain current output noise for the 100 over 100 micrometer graphene FET at three different gate voltage values. Markers present the extracted CDF of the random variable x equals to the natural logarithm of normalized noise, while the solid lines the theoretical CDF under the consideration that x is normally distributed. The precise fitting among markers and lines confirms that low-frequency noise data follow a log normal distribution, something that is shown for the first time in graphene FETs. The next two plots show the correlation of IV quantities such as effective gate voltage and drain current with low-frequency noise data for the same 100 over 100 device for two different gate voltage values. This correlation is insignificant, as you can see, and as we have mentioned previously, which is indicative of the fact that low-frequency noise data variations are caused from the fluctuations of number of traps NTR and Hodge alpha H parameters. Upper plots of this slide depict normalized low-frequency noise versus effective gate voltage for all the three devices under test. At each plot, black markers show the mean value low-frequency noise data, while purple and green markers the plus minus 2 sigma data values respectively. Smaller red markers show the data for all the measured samples. Solid lines represent the models, where black lines are the mean value model, while purple and green lines the plus minus 2 sigma models respectively. The behavior of the models is very accurate for both mean values and statistical plus minus 2 sigma cases, as you can see. Now, bottom plots depict variance of normalized low-frequency noise versus effective gate voltage, again for all three devices under test. Markers represent the data, solid lines the total variance model, while dashed and dotted lines stand for delta N and delta M variance contributions respectively. The fitting is very consistent, while the shape of delta N and delta M models prove that these effects act similarly as in the low-frequency noise mean value model. That said, delta N effect is responsible for the M shape of low-frequency noise variance, as it was for the M shape of the mean low-frequency noise, while delta M contributes near the CNP as it did for the mean low-frequency noise, while it retains its lambda-shaped trend. Low-frequency noise variance model parameters can be extracted from this plot. Thus, N alpha H can be extracted from CNP, while NTQF from the peaks of the M shape. Additionally, the new low-frequency noise variance model shows a deviation from the experimental data at high N-type conduction regime, probably due to delta R contribution to variance, which is not included in this study so far. In the left plot of this slide, the standard deviation of the natural logarithm of normalized output noise is shown versus effective gate voltage for all the three devices under test. Again, lines are the model, while markers are the data. Apart from the good fitting, it is worthwhile mentioning that the values of sigma from 0.1 to 1, as you can see, are quite close to CMOS devices of same dimensions, something that indicates an acceptable performance of the specific graphene FETs under test. Moreover, another crucial observation is the weak bias dependence of standard deviation data, with a rather smooth fluctuation near the CNP and a slight decrease away from the CNP, which is remarkably captured by the proposed model.
Excuse me, Dr. Mavrodekis, you have
NTCOF and
for
alpha
5 minutes more, please.
Are extracted from low-frequency noise variance data, as shown in previous slide. Regarding NTCOF, it was extracted much greater than unity for all graph FinFETs, which means the Poisson distribution, that is the case for trap statistics in silicon oxide transistors, as we mentioned before, is not valid in this study. This can be either because of the electrolyte graphene interface or the premature states of graphene FET technologies in general, as we have already mentioned. To investigate deeper the latter, low-frequency noise mean value model parameters, NTR and alpha H, are extracted for every available measured sample as it is shown in the right plot. Then the variance and the ln mean value of the extracted NTR and alpha H parameters can be calculated, and thus the low-frequency noise variance model parameters can be estimated by these equations. Astonishingly, these calculated parameters are exact the same with the values extracted from low-frequency noise variance data, as we saw before, confirming the accuracy of extracting these parameters from variance data, and in general, confirming the validity of the model. The table here shows all the extracted parameters for IV, low-frequency noise, and low-frequency noise variance model for all the devices under test. It was shown in this analysis that low-frequency noise deviations are not related with IV quantities, but strongly depend on fluctuations of parameters of the main mechanism that generate low-frequency noise, which are number of traps NTR for delta N and Hooge parameter alpha H for delta M effect. A physics-based low-frequency noise variance model is for the first time proposed with exceptional performance, where delta N and delta M contributors behave similarly as they did for mean value case. Finally, number of traps are shown not to follow Poisson distribution for the liquid-gated graphene FETs under test. I would like to thank you all for your attention.
Thank you, Dr. Mavrodekis. It was a very interesting presentation. And are there any questions from the audience? Yes, we have some questions from Anibal. The first question is, what is the impact of noise gate resistance on low frequency noise in graphene FETs?
Excuse me, you said the noise gate resistance?
Yes.
Okay, we haven't studied this in graphene FETs yet, but we know that gate resistance can also have a contribution to low frequency noise, but usually it's not very significant. But yet we haven't incorporated this part of the model in this work yet, so it's like a future work to study this effect.
Okay, thank you. There is another question. Can you please mention what you have studied low frequency noise in liquid gated devices? For which application this device has been used?
Well, we studied these devices because we had them available with some cooperations with the ICN2 Institute in Barcelona. So these devices are usually used in neural sensors in a human brain, but I'm not really expert on applications, so we just had the available data from these devices. We had some projects, so we investigated these devices for this reason.
Okay, for which applications these devices have been used?
Yeah, to my knowledge, they use them to some neural sensors, brain sensors and things like this, to sense neural signals.
Okay, thank you, Doctor. Dr. Eloy, do you have any questions?
Yes, thank you.
Thank you.
Dr. Mavrodekis, your presentation was pretty good. And I have just a question. Which are the figures of merit at high frequencies of the GFETs which are affected by low frequency noise?
Well, to my knowledge, low frequency noise can affect high frequency by upconversion to phase noise in such applications.
Okay.
So
which are continue, please.
No, please.
Yes. Thank you. Which are the strategies to diminish low frequency noise in GFETs? The main strategies.
Okay. So one way is to use, for example, specific substrates. So it is shown that boron nitride substrates have a very good effect, and they can eliminate low frequency noise. Yeah, more or less, this is what I know, especially for graphene FETs. And then what you can do is to choose some specific bias conditions where noise is not very high. So that is why we also study low frequency noise versus bias to see where it's maximized and to see where it's less.
Okay.
So yeah, more or less.
Okay, excellent. And just a last question. Which is the physical origin of low frequency noise in GFETs?
Wait a minute. So yeah, mostly in this work, we saw that low frequency noise comes from two main physical mechanisms. The one is the trapping in the oxide that I presented in the first slides, where a trap can be captured and then released, and this can cause a fluctuation in drain current, for example, and this fluctuation can also cause noise because current is fluctuated. Also, we said about the mobility fluctuation effect, which has to do with fluctuations of the mobility. And this is described by the empirical Hoods formula. So yeah, more or less, these are the two main effects that are the physical mechanism of low frequency noise.
Yes, of course. The latter mechanism is pretty interesting because it is claimed that in graphene, the transport is almost ballistic. Which are the origins of the mobility variations in graphene? That's a question I want
to be honest, this kind of devices that we have studied, the channel length is not so small in order to speak about ballistic transport.
Okay.
But 1 minute. Yeah, so 1 minute. Let's see. Yeah, more or less, this. One other thing that we know is that in graphene FETs especially, the mobility fluctuation has to do with the number of layers. So the higher the number of layers, we have more intense mobility fluctuation. But in single layer devices that we study, it's not so intense, but still it can have a small contribution, especially near the Dirac voltage.
Okay. Thank you so much.
Thank you.
These are all my questions. Thank you. Thank you, Doctora María Elena.
Thank you, Dr. Eloy. There is no more questions. The last, Dr. Ivan Puchades asks, could you briefly show again how the mobility was extracted?
Okay, you mean for which of the two kind of devices? But okay, yeah. Let me go. Maybe I can. So yeah, for the extraction of the mobility, more or less, we are using a simple linear method for the linear region, where the mobility is extracted in the area away from the CNP. I don't know if this answers the question or not.
Dr. Puchades?
Yes, thank you. Yes, thank you. That's all I wanted to see where that was directed. You showed
Yeah,
some,
more or less. For example, here it's around this area from the linear region. Yeah.
yeah, you're showing some nice numbers up to 7,000 centimeters squared per volt second. So that's very good results.
Okay.
Okay, there is no more questions. Dr. Mavrodekis, we're awarding you this diploma. I'm going to share it.
Should I stop sharing me? Yeah. Okay.
Okay. El Instituto Politécnico Nacional, Cátedra Eugenio Méndez Docurro, otorga el presente reconocimiento al doctor Nicholas Mavrodekis por su participación en el seminario en línea High Frequency and Terahertz Devices and Circuits, Perspectives on Emerging and Advanced Technologies, Part 1, con la conferencia 1/F Noise Modeling in Microwave Graphene Transistors, llevada a cabo los días 26 y 27 de noviembre de 2020, la técnica al servicio de la patria. Thank you very much, Dr. Mavrodekis.
Thank you very much.
Thanks to the audience for your attention. We invite to the public to tomorrow's conference. Thank you.
Doctora Marilena, is
Sí, dígame,
still
doctor
missing
Eloy.
the presentation of Dr. Puchades.
Yes. yes, of course. Please, Dr. Iván Puchades, could you please share your presentation?
Yeah, thank you. Can you see it? Is it showing?
I'm going to introduce you first, please.
Okay.
Dr. Iván Puchades joined to the Electrical and Microelectronic Engineering Department as an assistant professor in the fall of 2016. His current research interests include collaborations to explore high frequency and sensing application of new materials such as carbon nanotubes and other nanomaterials such as graphene, 2D metal chalcogenes, phosphorines, borofin nanowires, etc. He's also interested in expanding research of MEMS devices. In 2016, Dr. Puchades completed a 2-year IC fellowship with the Chemical Engineering Department at Rochester Institute of Technology under Dr. Brian Landy. From 2011 to 2014, Dr. Puchades was a research assistant professor at RIT. His research focused on MEMS devices, particularly in application of thermal, electrostatic, and piezoelectric MEMS resonators, piezoelectric energy harvesting, multi-sensor networks, and system integration. He also taught undergraduate courses in electrical engineering and graduate level microelectronic engineering courses in MEMS design, fabrication, and test. From 2000 to 2005, Dr. Puchades worked as radio frequency device engineer and BiCMOS technology development engineer for Motorola and Freescale Semiconductor in Phoenix, Arizona. He was responsible for CMOS and high voltage technology integration at the 0.18 micrometers node and later resolution of several device engineering issues. Welcome, Dr. Puchades from Rochester Institute of Technology. Our speaker represents the topic terahertz communication based on graphene device. Doctor, you have 30 minutes for your exposition. After this, we will have a question session of 15 minutes, and all the questions go to the end of the exposition. Dr. Puchades, please start your presentation.
Thank you very much, Dr. Acevedo. First of all, I want to thank the organizers for inviting me to this webinar. I want to thank the Instituto Politécnico Nacional. It's an honor. And as Dr. Acevedo said, I'm in Rochester Institute of Technology, which is in Rochester, New York. And my talk is going to be, I changed the title a little bit to represent the presentation a little bit better, but we're going to describe graphene-based devices for terahertz communication systems. So the overall the arching theme is the same, just a little bit spin on a different way. But anyway, before I get going on the technical aspects of it, I want to show where Rochester is. So if you look at New York City in this map, hopefully you can see my pointer, my laser pointer. But New York City would be located in here. Rochester is in the state of New York, closer to the border with Canada. We're near Niagara Falls, and there's a lot of nice places to visit. So I welcome anybody that is in the audience to come see us. Here's a aerial view of the campus, and we're located in the back here. And we have some nice facilities and a clean room where we do a lot of this work. We're a university with about 20,000 students. And as you can see, we have mainly undergraduate, but also some graduate students. And here's our undergraduates having some fun with what they call humans versus zombies event, where they all chase each other around with Nerf guns. And here's a picture of what things are going to look like in the bottom right corner, what things are going to look like in a couple of weeks up here, where we'll get covered with snow. So if there's any skiing fans out there, this is a good place to be for enjoying some winter sports. All right, so that's the quick introduction on what's going on in Rochester. Here's an outline of my talk. I'm going to start by talking about the case for terahertz communication systems. What is the motivation for doing this work? Some of the applications on those systems, some of the challenges that the hardware still has, some of the hardware challenges. And then we'll briefly touch upon a solution which includes everything made out of graphene. So everything graphene for an RF communication system. Then we'll talk about two specific aspects of it, which is the oscillator, so graphene-based oscillator and source, the efforts that we've carried on at RIT, and then a modulator as part of that system. The antenna, we still have not been working on it, and the linking components between all of these have not been developed yet, but that's we'll talk about those as well. So jump into the motivation. So as we all know, wireless communications have been growing rapidly. 5G is being deployed currently. And here's some numbers. They have 8.8 billion devices, 13.1 expected by 2023. This is in billions. Not only there's a lot of devices, but we also need faster connections. 5G, it's up 20 gigabits per second. If we look at the evolution between 1G to 5G, we've gone up from 1 gigabits per second for 4G to expected 20 gigabits per second in 5G. But this is 2018, 2020 we're on now. What's going to happen in the future? Well, we'll probably go on to 6G. What is 6G going to be? Well, one of the proposals is that we're going to be at terabits per second. And to do that, we're going to need terahertz technology. So terahertz technology actually looks at the spectrum sees an opportunity here to introduce an area that has not been utilized. So if we look at the current RF technologies, they're all bunched in here between 0 and maybe 0.1 terahertz. If we look at the optical systems, they're all in the higher terahertz as far as the frequency goes. So there's this big gap here between half a terahertz all the way to 10 terahertz, which we're calling the no man's land. Okay, it's a high frequency, not high enough to be optical, higher than current electronics. And there's a nice opportunity here with a lot of open bands for very high frequency communications. The fact that it's very large available bandwidth as well alleviates the spectrum problem, so allows us to do things or alleviate that spectrum area. And the applications that you can see in here are short range communications, such as virtual reality communication. A lot of the virtual reality applications nowadays are lagging in terms of quality and detail on the representations. That's because there's not enough data to really represent things as they should be. So this could get away from having any tether to your computer in the short range. Here's another picture here, which we're also showing. The short range communication could be done with terahertz links, very high data transfers. But not only there, also in the backhaul, so in the final delivery of the information in line of sight situations, you could also use terahertz. And it has been shown that even though there's some water absorption at that frequency, you can find certain bands where you still have very low water absorption and obtain very long distance communication systems. In the same sense, you can also think of the satellites talking in terahertz and then downlinking at a slower rate down to your hosts. Another possible solution application that this is geared towards is that you can make very small transceivers and antenna, and there's 1 millimeter. You're not talking the terahertz being such a short wavelength. You can make very small devices. So you can also do with that aspect. You can do chip-to-chip communication or device-to-device wireless communication. You don't need to use copper wires to connect anymore. You can do that wirelessly. And you can also start looking at the bio aspect of it. So you can communicate through some tissue layers internally at that frequency. And there's other things such as brain neurons and so on that can be applied as well. So two aspects, I guess, will be high data transfer and also small sizes. So hopefully I've convinced you that it's worth pursuing and that it's worth working on. The problem now is that there's a lack of hardware to do this. As we showed earlier, there's a gap in there, and we gotta close that gap. There's two approaches to close that gap. There's the electronics approach, which we're actually pushing the limits of the electronics up. The examples here are frequency multiplying chains, resonant tunneling diodes, and some vacuum electronics. And the advantage here is this is high power. But again, we're coming from low frequency, multiplying it to get up to the terahertz regime. The photonics approach is to come down from their high frequencies. And this is where they're in the hundreds of terahertz. They have to come down to the single terahertz. And what we do in here is actually cut down the frequency or even use some quantum cascade lasers or some photoconductive antennas to get slower because they're too fast. Our approach here is to use some of the new 2D materials, which are intrinsically in the terahertz. And our approach is to use graphene materials. And the idea is to do everything monolithically in one chip. So on-chip graphene-based plasmonic receivers, antennas, and antennas arrays. Okay, so as Dr. Feijó has shown, and our previous speaker as well, graphene shows promise because it has a high carrier mobility, it's a semi-metal behavior, and it's more importantly compatible with seamless processing. So it makes the processing much simpler. So as I described before, there are three components that we've been working on, and these actually are the backbone of a basic radio frequency communication system. You need a source or an oscillator, okay? And we, in the literature, graphene has been shown to produce surface plasmonic polaritons in the terahertz range. So this is a candidate. A modulator, and in the literature, graphene have been shown to absorb some of this SPP waves based on an applied voltage across it. And we need an antenna. And again, graphene has been shown in the literature to be able to transmit generated SPP waves into space. So the idea is to make graphene, make all this out of graphene, okay? And also the links between the components. So between the oscillator and the modulator out to the antenna, how are you going to carry those SPP waves at the terahertz? You're going to need a high carrier mobility material. So graphene may be able to do that. All right, so describing a little bit what the literature shows about the making oscillators. Here is a paper from Dr. Journet, who's now at Northeastern University, which indicated that on a 2D electron gas channel, you can actually, if you set your source and drain impedances correctly, you can generate a standing wave. And if you get those dimensions correctly, that standing wave will be at a terahertz frequency. That standing wave could be emitted out and at a terahertz. So looking at that, he also tried to determine what are the right impedance conditions. And he looked at the capacitance at the source and at the drain terminals of the components. This is some simulation that he performed. And he said that if your capacitance at the source and the drain are equal, well, you don't really get much resonance. But if you make the capacitance at the source much larger than the capacitance at the drain, and remember, capacitance is the inverse of impedance, you do get resonant as the carriers that are generated at the source bumped with the higher impedance at the drain, and they get sent back. They kind of bounce back and forth as they can escape out of the channel. So that's what the basic physical phenomena is that is taking place. He also looked at the energy that this would produce, the radiated electromagnetic power per unit channel. And based on the simulations, he determined that he would get about 4.2 times 10 to the minus 8 watts per micrometer. So if you want to get any meaningful radiation out of these devices, you at least need to 1 milliwatt. So you have to make these devices quite large in terms of their widths. So having all that in mind, this is what we proposed. We proposed a graphene, basically looks like a graphene FET with a source and a drain and a gate. This gate here is used to initiate the vibrations, the oscillations, and really in theory, you only need to initiate it once. Once you get it going, they should sustain, but we know there's going to be losses. So some sort of lock-in amplifier or lock-in mechanism to amplify the frequency as a driven frequency would be necessary. If we look at the impedance conditions that were determined by Dr. Journet, we can use the equation that represents the capacitance between metal lines as the capacitance between the gate and the source, and the gate and the drain will be determined by that. And we can determine what the distance would be playing with that capacitance. It will be determined by the distance between the gate to the source and the gate to the drain. So as you can see in this example, we're saying, let's make a source that it's a lot wider than the drain, and also put it closer to the gate and the drain farther away from the gate to get those capacitance values. Now we need to make it large because we said that the energy produced was pretty low. So in our proposal, we're gonna put 2,648 of these devices in parallel altogether to produce that much energy. So we could do that two different ways. We could do it by changing the sizes a little bit, and also making this funneling effect of the graphene. The graphene will be in the green, so that funneling effect, we can do it two different ways. And again, we can play with the distances. So here's are 3 examples of where the impedance of the source is always smaller than the impedance on the gate. But as you can see, there's different variations. The design number 3 is more of a square. The funnel is much sharper, if you wish, as compared to design 2 or design 1. Design 4 is where we say, well, let's make this an exaggerated or an extreme case, where if you can see in here, the sources are extremely large and the drains are extremely small. The sources are 1,000 microns in width, the drains are 40 microns in width. So that's another extreme. We actually are in the process of fabricating this, and a lot of this work was done by a senior project by Sarah Taylor, and we have some upcoming results, but as far as we took it. On the next front, we have the modulator. And again, this has been shown in literature that you can obtain graphene plasma modulation at the terahertz frequency. And this is work from 2012, where the voltage across a graphene layer that was illuminated with a terahertz signal was able to modulate the terahertz signal that was reflected back. Okay, so if what we're showing here is a normalized reflectance. So 1 would be that all the signal was reflected back. So if your voltage across the graphene layer was between -20 and -10 volts, the whole signal was reflected. As you change the voltage across the graphene layer, more of that signal was absorbed. Okay, so this shows that you're absorbing some of your terahertz frequency. And guess what? You can then modulate your terahertz signal that way. All right. Here's an example of how that would be done in a monolithic device. So here's a graphene film bringing in an SPP layer. So this is a plasmonic at a terahertz frequency. As you go over this region, this is your modulating region. You have an electric field across your graphene, not directly connected to the graphene, but an electric field across the graphene. And you could make that graphene absorb some of this signal or not. And then you're modulating your terahertz signal that is produced by your oscillator or your source. Okay. And this is our approach. So this is again by Dr. Jornet. That's theoretically how that will be done. This is not ready yet because we don't have a graphene source. So an approach that we used was to have a terahertz optical source illuminate a device which has a graphene layer encapsulated between 2 electrodes. The top electrode is a set of metal fingers. The bottom electrode is a buried P+ silicon. And by applying a voltage across these 2 electrodes, you're effectively creating an electric field across your graphene and hopefully changing the amount that that graphene layer absorbs. Okay, how we fabricated this in a master's thesis a few years back, and this is a process flow that we proposed. We start with silicon, we put in some contacts, then we did an implant, a phosphorus implant on the silicon. So this is this P+ layer. Then we grew an oxide. You can grow a thermal oxide in this case because your silicon is available. And we choose 3,000 angstroms so that we could see the graphene that it's on top. We could have chosen 900 angstroms as well. That's another thickness that would have been more efficient per se. And then we put in the graphene down. We use a PMMA mediated process. We're in the process of developing another process of doing that, but the graphene was put down. Then a dielectric on top of that graphene so that we could put the contact fingers right on the top to create the capacitance to apply that electric field. Before the metal fingers were put down, we etched some contacts down to the P+, and then we lift off process for the metal fingers. So that was the fabrication itself, but that wasn't it. Then we also had to package this so that we could test in a real communication systems, as I will show in the next slides. Some details on the Modulator Design. This is the mask that we use, and we actually made them quite big because we had to illuminate this with an antenna source that had quite a wide beam. So we made this 5 millimeters by 5 millimeters, and this is showing that in the first quadrant, we had 1 micron lines and spaces. On the second quadrant, 1 micron lines, 2 micron spaces. And the third quadrant, 1 micron lines, half micron spaces. And on the fourth quadrant, 1 micron lines with varying spaces. The transfer process was critical, and we did a lot of work on investigating how to do that more effectively. And here we are showing the process that we follow. This is a wet process, a PMMA transfer process, and this has been published, but the results are not really that easy to implement. So we ended up having this done by a company that specializes on these transfers for our devices. At the same time, now we're looking at applying a lamination transfer method, and this is based on a recently published paper where basically you just start with the graphene on copper, you soak it overnight so that the graphene and the copper oxidize and they start to come away from each other. Then you laminate that on a PVA film, which is water soluble, and then you laminate that onto your silicon substrate, and then you remove that water soluble amount or film, transfer film. The Raman spectroscopy that I'm showing in here is normally used to quantify the quality of your graphene, and having a second peak here higher than your first peak usually indicates that you do have single layer graphene. When they're more equal to each other, like on this bottom picture, it indicates that you might have multiple layers of graphene. So what I'm showing in here is that our lamination process may produce slightly better or higher quality graphene than the PMMA water mediated process. So that's an improvement on our process. In any case, we were able to fabricate these devices, and this shows the last step where we laid down the metal fingers. And the challenge here is that these metal fingers only being 1 micron in width, they have to be uniform, and the whole length, the whole 5 millimeters of them has to have no breaks. And that proved to be a challenge for these large area devices. We did this on 6-inch wafers, so you can see the entirety of the wafer. The graphene film was placed about 2-inch by 2-inch in the middle of the wafer, and then the metal fingers, you can see the 4 different designs on the surface. A little more of a close-up picture. You can we see the metal lines here with the spacing between it, just as we wanted it to be. This is 1 micron lines, 1 micron spaces, and the slight deviations from the intended results. And this is a close-up picture where you can see the graphene film and its defects. That's one of the big issues about graphene films, that in many cases they're not uniform throughout the entirety of them, especially for large area transfers. So that's something to keep in mind as you're making devices that are larger than the lab grade devices, which are only in the few nanometers range. As you're going larger, you're going to have more challenges on that. In any case, we were able to complete the fabrication, and the last part was to test it. Now, before we could test it, we had to dice up the devices. So in this picture, I'm showing just the final chip itself. So it's separated from the wafer. And we also had to package it on a way where we could actually access the contacts and create that electric field between them. So we wire bonded it to a PCB, the copper PCB board. So you can see here the wire bonds connecting to the top electrode and the bottom electrode for all the 4 different versions of the devices that we have in here. And we took this to the University of Buffalo Dr. Jornet's lab. He's now at Northeastern, but his system provides a terahertz signal that it's up converted from a 250 gigahertz signal that is produced electronically. So it's not an optical system, it's an electronic system, and he actually has an antenna that produces the signal. So here's a picture of the antenna and the test setup. So this is the source. The terahertz signal was sent wirelessly to the modulator, and then it bounced back to the receiver. And these connections here were used to apply that electric field across the graphene. And we monitor the reflected signal, and the results showed, as we're in this picture here, the results show here that for 0 volts applied, the signal that was picked up by the receiver is in the blue. Okay, so the amplitude of this was 125 microvolts with respect to a signal that was sent, 1 millivolt signal. Then we applied 9 volts across that graphene, and we saw that the signal now received had decreased to 110 microvolts. Then we increased that to 12 volts, and we saw that the signal was decreased to 80 microvolts, and at 24 volts, it had been decreased to 20 microvolts. So we definitely saw modulation of that received signal. And what we're seeing here is really the terahertz signal, right, as it goes up and down in voltage as it's received. So this is a real measurement of a terahertz wirelessly transmitted signal. If we applied a bunch of different voltages, and we plotted it versus the reflected powers in dVm, and as you go low in your voltage, you're not modulating your graphene, and as you go higher, or your signal, as you go higher in voltage, you start to absorb some of that signal that is sent back. And this actually matches what was accomplished with an optical system back in 2012. So we're pretty happy with those results, but we do have some improvements that we want to make. We want to encapsulate the graphene with hexaboronitride. I think that would result in better results. The contact cut layer, we had an issue here where we think that the graphene might have been shorted in some of our devices. Liftoff process, we want to improve the resolution lines. And then we also want to protect the devices as we're wafer sawing and singulating the chips, because sometimes we do have some defects that could affect the device performance. To put it all together now, the modulator and the source, we've come up with a process where they could be fabricated in the same chip and at the same time. And this was developed by Sarah Taylor. And here's a cross section of what those devices would look like. As you can see, a lot of these layers are the same. We have the graphene layer, we have an oxide insulating, and then the metal layers right on top. So there's no reason why we couldn't do this at the same time. Here's a process flow on how that would be done. You would start with your silicon substrate, implant the bottom plate for your modulator, grow an oxide on top, deposit a hexaboronitride layer. This will make sure that the graphene that goes on top, it's nice and well preserved and preserve its qualities. Then we could pattern that graphene just to separate the two, or we could actually leave a link between the two. So if we're creating the oscillations on one side, they can be transferred to the modulator, and we don't need that external terahertz source anymore. Then we would put on either a TIOS or that ALD. Aluminum oxide has shown to be a very good insulator.
Excuse me, Dr. Puchades, you have 5 minutes more, please.
Okay, I think that would be just
Thank you.
perfect. And then let's see. So we put an insulating layer and then cut some contact cuts. And again, the last step here would be to put metal connections, and metal connections will result on the final structure that we're intending. the source with its 3 terminals, and the modulator with the electric field across the graphene to modulate the signal. Okay, so that was perfect timing because I've come down to the conclusions here. So the terahertz communication systems are expected in the near future, and they're necessary for 6G applications. There's work on different exotic devices, which are by themselves going to become expensive. So using graphene in a monolithic way, it lowers the price of those devices and makes this technology available to the wider community. So that's one of our goals as well. The hardware needs to be developed and implemented, and not only in the lab, we also need to start doing some real testing with real wireless signals. We have demonstrated a modulator based on graphene. We're working now hard to integrate all the other components, such as the source and the antenna, as well as the links between them. And we believe we can do it all with graphene. And this is on a collaboration with Dr. Jornet at Northeastern University. He is an expert at terahertz communication systems, and he is really providing a lot of feedback on our systems. And that's it. That's all I had. So if you have any questions. Well, Dr. Acevedo, I believe you're muted.
Yeah, sorry. Aníbal asks, you mentioned that defects in the graphene channel can degrade your device's performance, but what about traps with oxides? Do they have an impact on the terahertz devices?
Yes, all defects, defects and traps and graphene discontinuities, they're all going to affect the terahertz, the performance of your device. They could affect it in different ways. I believe for the source, they may actually shift the frequency at which it resonates. We have some preliminary simulations that indicate that. In the modulator, they could affect the way that your signal is modulated. So yeah, all those need to be studied and understood.
Thank you. Miguel asks, what modulation technique is used in the modulator?
So right now, the expected technique is to just be an amplitude modulation. That's what we're showing as the most effective. But you're right, there are other more complex modulation techniques that are more applicable to higher frequencies. And for this demonstration, it was just an amplitude modulation, but phase modulation, some other more complex techniques will be necessary. And Dr. Jornet, actually, if you look up his papers, he's got some good ideas on that.
What is the throughput achieved?
Throughput in terms of yield, or throughput in terms of power?
In terms of yield.
Yield. Yield in terms of fabrication, how many of these devices are actually successful? The yield is low. We got maybe 3 modulators out of that whole 6-inch wafer that actually works. So 3 out of many, 3 out of a few hundreds. And we believe that the reason for that is because we did not use a hexaboronitride sublayer. It was just a graphene on SiO2, which we have learned since then that is not the best practice. We actually did see a time effect where a modulator that worked one day, 2 weeks later did not work because of that graphene mismatch with the SiO2. Well, that's what we believe the problem was. So hexaboronitride is key to make these devices work.
Okay, thank you. Everybody is giving you congratulations. for your excellent presentation, Dr. Puchades.
Well, thank you very much. It was a pleasure.
Okay. Dr. Eloy, do you have any questions?
Yes. Thank you, Dr. Maria Elena. Dr. Puchades, thank you for your outstanding presentation. I was deeply impressed by your excellent results you showed. I have a couple of questions. First question, which are the targeted bands to conceive terahertz communication systems in these studies?
Mm-hmm. So the system that is actually available, it's at center frequency of 1 terahertz. So that's the center frequency. As far as the bands, we haven't really studied them, but I think it's expected that you can have bands in the hundreds of gigahertz.
Hundreds of gigahertz. Mm-hmm. Yes, that's my next question. Which was the speed of the data transmission in your first tests?
So it was basically a DC, just the demonstration. Yeah,
just a demonstration of the carrier.
Right. Yeah, just a demonstration. Those biases were just a DC, so there was really no active modulation. It was a static modulation. We're hoping to get some active modulation on our second round of tests. And that's when we went back to the lab 2 weeks later, and our graphene seemed to have relaxed and it wasn't really modulating anymore.
Oh, okay. Understand. And what about the antenna technology? Which was the antenna technology you used in these tests?
So the antenna that is on the system at Northeastern University, I'll show you. It's basically a horn antenna.
A horn antenna.
Yeah. Now,
okay.
So when we go to develop the graphene antennas monolithically on our substrate, we'll probably look at a patch antenna or even a just a simple monopole antenna, I think would be applicable.
Oh, okay. Yeah. Pretty well. Mm-hmm. Well, I thank you again for your presentation. It was pretty interesting. Thank you so much, Dr. Puchades. Thank you, Dr. Maria Elena.
Thank you, Dr. Eloy. Thank you to you, Dr. Puchades. We are awarding you this diploma. I'm going to share it. El Instituto Politécnico Nacional otorga el presente reconocimiento a Iván Puchades por su participación en el seminario en línea High Frequency and Terahertz Devices and Circuits, Perspectives on Emerging and Advanced Technologies, Part 1, con la conferencia Terahertz Communication Based on Graphene Devices, llevada a cabo los días 26 y 27 de noviembre de 2020, la técnica al servicio de la patria. Thank you very much, Dr. Puchades, for your presentation.
You're welcome, and thank you very much for inviting me.
Okay, and that is all for this part. And we invite to the public for tomorrow's conferences. And thank you for everybody. Okay.
Thank you, and see you tomorrow.
Okay. See you. Bye.